All right, let's keep going. So now we're going to talk about things beyond one dimension. I stole a minute from you, but you get minutes from me all the time. 3D or not 3D? That is the question. All right, 3D or not 3D? We're going to talk about waves that are 3D, but are they 3D? It's hard to say. Okay. The string wave. Was it 3D or was it not 3D? The string wave is, maybe it's 2D. No, is 1D because it only varies in one dimension. Because it only varies in one spatial dimension. I mean spatial, right? It only varies in x along the string. I don't have dimension yet. I'm getting there. Right? String waves 1D, right? Now you could say, oh, but wait a minute. But it's a transverse displacement. Right? If you think about how it really works, this big D, the D of x and t, is really in another dimension. It's not along the string, is it? Right? Yes, I know. I'm trying to not. Yes. I'd be a horrible lawyer. No. It's not 1D. Okay, so this gets into the question of if you take some lesser course about waves, the first thing they're going to say, the first thing in your stupid book is, let's classify waves as transverse or longitudinal. Okay, that is the least interesting thing in waves in all of physics in the whole universe, is whether waves are transverse or longitudinal. Okay, it's always the first thing they bring up because it's easy to think about and it's easy to write homework about, and you don't have to do any math. And I hate it. Okay, so I'm sorry. So string waves are transverse. Okay, but it doesn't make them two-dimensional, is my point. They're still one-dimensional because when we wrote this equation, a sine kx minus omega t, we wrote it multiple times. It only depends on x. It doesn't depend on this transverse direction. That's just the disturbance. So mathematically, what makes a wave, what its dimension is really just how many variables, spatial variables, show up under the sign. So that's why we would say a string wave is one-dimensional, even though it's transverse. Well, who cares? Okay, but now it's going to get more confusing. Okay, because we're going to look at waves that are sold as 3D, right? A plane wave. So this part of the class has like vocabulary to keep up with. What makes a plane wave, there's many kinds of plane wave. It's not just a certain thing, is that it travels uniformly along a Rene Descartesian axis. That's really technically what a plane wave is. It looks a lot like the string wave, doesn't it? How is it different? So the way it's different is, let's do an example. Let's do a sound wave that is a plane wave. Right? All sound waves don't have to be plane waves. You can have sound waves that are plane waves or other kinds. You can have light waves that are plane waves or cylindrical waves. But let's just do an example of a sound wave that is a plane wave. It would look like this. Mathematically, you would have the pressure as a function of just x and t, one-dimensional, equals the pressure amplitude times the sine of kx minus omega t plus some phase constant. We'll worry about that later. So you say, well, that looks pretty freaking familiar here, right? A is constant amplitude here. P naught's a constant amplitude there. Kx, omega t, phi naught. So what makes this a 3D wave? Or is it a 3D wave? That's why it's a question. Okay? So let's think about it here. Let's draw this mathematically here. So here we have somebody making a sound, right? So this is Kesha from the last lecture. She's got some weird eye makeup going on. Kesha. Right? And so she's making a sound like this. Oh, wait, she got rid of the dollar sign. I'm sorry. She got rid of the dollar sign. It's just Kesha. There we go. Actually, I think we should go with the cent sign, considering she got sued. So I would call her Kesha. I love Kesha. I'm sorry. I just, so much usefulness out of one person. Right? So this is x, and what is this? So the point is the plane wave, p doesn't have a direction in space, is it? It's a scalar. It's not a vector. So it's not like a displacement in a direction. You don't have to say, wait, is the displacement in y or is the displacement in z? No, it's just a pressure. So what you would say is everything along this plane that's riding along with this peak has high pressure. And then everything riding along here with this peak is like a plane with low pressure. All right? And then when you get back up to here, the pressure is 0. Or actually, for a sound wave, it's atmospheric pressure. You go above and below atmospheric pressure. But as you're going up high and you're going down low, basically, what the key is for a plane wave is that the I'll say the value is constant along a YZ plane. For this example, right? We have it moving in x, so this would be y, and that's z. So in any YZ plane, it has the same pressure. Not all the time. At an instant in time, this is high pressure, this plane, and then this plane is low pressure. But if you wait half a cycle, this will be high pressure, and this will be low pressure for a whole plane. Okay, so in that sense, it is 3D. It's more 3D more than the string wave is. It's not that the physical thing is happening in multiple dimensions, it's just that it's constant over this plane. All right, so let's have a quick look. I can show you maybe a slightly more clear illustration of what a plane wave looks like here. I got one more to show you from back when I cared and did lots of animations for sophomore physics when I was only 35. Let's see. So here we go. Right, so there's the plane. This wave is going to propagate along z instead of x, this deal. Right? And as it moves forward, it would get to this point, say, and all the arrows would be up. Oh, no, it's going to be off. And then down. Oh, the animations don't work. Oh, never mind. Okay. It was beautiful. Trust me. Go read my course reviews from 12 years ago. It was amazing. Okay. They changed the aspect ratio of like screens now, and none of the animations work anymore. Okay, so it's you people in your wide views' fault. It's this.